Okay, so this section is going to be on computational complexity. Okay. Now, when dealing with computational complexity, there's two different branches. There's what's called time complexity, and there's what's called space complexity. Okay, so time complexity deals with, let's say, analysis of the number of simple, sometimes referred to as atomic, operations, analysis of the number of simple operations needed to perform an algorithm. To perform a given algorithm. Okay, so here, when I say simple or atomic operations, I mean things like comparison, addition, subtraction, things like this. Multiplication. So comparison is like a Boolean comparison between objects. Division. So these would be like atomic operations, simple operations. So time complexity is concerned with the analysis of the number of things needed to perform a given algorithm. Okay. Space complexity is refers to the analysis of the amount of memory a given algorithm requires analysis of the amount of memory a given algorithm requires to perform or something like this. Okay, so these are the two branches of the analysis of algorithms, which is broadly referred to as computational complexity. Now, here, space complexity, this, we won't study this. We're not going to look at this at all. This is something that would fall under the umbrella of a course like a data structures course. So a data structures course which studies space complexity. Hopefully study space complexity. But in a course like discrete mathematics, we will focus on time complexity. Okay, so both of these, though, both of these topics really are just trying to measure how efficient an algorithm is, or is an algorithm feasible? For example, let's consider, like if an algorithm takes, if you have an input list of size n, So n elements in a list, and the algorithm does something to that list. And it takes n factorial atomic operations, then this is not a really feasible algorithm. By the time you get to a list that's reasonable in size, like 1,000 factorial, that's not going to be efficient for any hardware to solve. So this analysis of algorithms kind of like, it gets rid of the idea of hardware and just looks at space and number of operations. Okay. So let's look at an example. And again, we're going to be focusing on time complexity. Right, so let me pick out just a random example. Okay, so let's take an example. So describe the time complexity let's say we're finding the maximum element in a finite list of numbers. Okay. We will use for this example, we'll use comparisons as our atomic operations. So let's first look at the algorithm. We'll call it find max. Okay. And let's say we'll have our input. A finite list L of numbers. We'll say there's n of them. So, and then our output will be max, which is the max element in L. Okay. So now let's look at the actual algorithm. Okay, so the way that this algorithm works, if you watch my lectures, we assume that, we'll just say that, we'll assume that max is equal to A1, the first element in the list. And then we can say for I equals 2 to n, if max is less than AI, then max is assigned to be AI. And then finally, we have return max. Okay, so this will find the maximum element in a list. It assumes it's the first one, and then it checks to see if the next element is bigger, so forth and so on until we get to n. And then after we get to n, we've exhausted through each element, and we would find the maximum. Okay, so When describing the time complexity of this, so we will say, so the solution maybe, so using comparisons as our atomic operation. All right, so we measure how many comparisons happen during this algorithm in terms of n. Well, so when entering into this, so we have an assignment right here. Okay, so we have an assignment, and then here we have I from 2 to n. Okay, so imagine we enter into this algorithm that I is equal to 2. Okay, and then we compare, is max less than AI, right? That's one comparison there. But then we have to check, after we make that comparison, maybe we do an assignment, maybe we don't. But then we have to check, is I greater than n, right? When we get back up to the for loop. So we have one comparison here, and then we have to compare I against n. So it's like there are these two comparisons and I is equal to 2, right? Like there's this comparison right here, and then we have to check, is I greater than n? And then if I isn't greater than n, we increment to I is equal to 3. And then we have to check again, is max less than AI? And then we have to check, is I greater than n? Okay? So we see for each of these I, from 2 to n, we have to make 2 comparisons. You see that, right? A comparison is a Boolean comparison, like is max less than AI? And then is I greater than n? Or does I equal n, right? So for each of those I, from 2 to n, we make 2 comparisons. So it's like 2 plus 2 plus 2 plus 2 plus 2 for each I from 2 to n. So what does that equal? That's 2 times n minus 1 comparisons. So using comparisons as our atomic operation, we see find max uses 2 times n minus 1, or just 2n minus 2 operations. Okay? And if you've been watching my previous lectures on big O notation, we would have something like hence find max has order big theta of n. It's order n, meaning it's big O of n and also big sigma of n. So roughly, if you have, so what this is saying is that if you have an input list of size n, this find max algorithm is always going to run as a function of just n itself, roughly. Which means it's efficient. It has linear runtime. Like if you put in a list of a billion, it's going to take roughly a billion operations to find the maximum. Okay? if you put in a list of 1,000, roughly 1,000. It doesn't grow too fast, right? So, and the reason why I'm able to say that it's big theta of n is because this right here is a polynomial, and as I mentioned in a previous lecture, polynomials are always order n, or order the degree of the polynomial. Okay, but at the very least, if you didn't want to use that, you could say that at the very least you could do hence find max is big O then. If you weren't caught up on the theta notation. Okay, so let's look at another example. Okay, so maybe see. Oh, if we go back to our searching algorithms, so there was this linear search algorithm that I described. So linear search. So input, we have x, which was an integer, and then a list L of integers, distinct integers. Output I, which was an integer, index, where if I wasn't equal to -1, then A of I is equal to X. And if I was -1, then it wasn't found. So then the algorithm looks like this. Okay, so we say I is equal to 1, and then we have a while loop. While I is less than or equal to n, and a sub I is not equal to x, we're going to increment I. So I is equal to I plus 1. Okay, so then at the very end, we have an if statement. So if I is less than or equal to n, return I, else return -1. Okay, so this is the linear search algorithm. It's an algorithm all of you should know. Or maybe not if you don't know it, hadn't learned it yet, you should know it now if you're looking at this. And just remember it as you continue on in your education, so that in case you get asked in an interview, you can state it. Okay, so let's look at the number of comparisons here. Okay, it seems like there's like, okay, so for a given example, right? What if we found AI immediately, right? Like if I was equal, so like for example, if A1 was equal to X, then this while loop would only happen, it wouldn't. This would never enter in there. and we'd skip down here, we'd do this comparison, and we'd exit out. So what we're going to be concerned with in particular is what's the worst case? That was like the best case, that the very first thing in the list is X. We want to look at worst case analysis. So among all the possible ways that this algorithm can run, what is the worst? Well, the worst is that X is not in the list. And if X is not in the list, then we have to search through each one of those positions all the way through until we find out that it's not there. So that's the worst case. So how can we do this? Well, so when I is equal to 1, right, we have to make a comparison there and a comparison there. So again, this is looking at Boolean comparisons is our measure, our atomic measure, atomic operation. So we have 2 there, and then we increment I, and then, so when I is equal to 1, we have to do 2 comparisons, and then when I is equal to 2, we have to look at those comparisons again, right? And it looks like for each I, 1 through n, we have 2 comparisons, right? For each of those i's, 1 through n. If it wasn't in the list, we go through all the i's up to n, right? So this is just kind of like scratch work. So for each I equal 1 through n, we have 2 comparisons. Right? There and there. And then at the final step, we have that I is equal to n plus 1 at the very last step, and we compare there, and then we break out. And then plus 1 comparison when I is equal to n plus 1. We compare there and we break out. Okay? And then we compare there 1 time. And then that would break and then we go to that return. And then plus 1 comparison for the if statement, or if else statement. Okay. So how many in total? So we have, for each I, 1 through n, we have 2. So that's 2 plus 2 plus 2 n times. So we have 2n, and then we have plus 1, and then plus 1, plus 2. So hence, there are 2n plus 2 comparisons needed. So linear search has complexity, has time complexity, big O of n. Because that function there is big O of n. Okay? Okay, so that's again looking at, when you're looking at measuring time complexity, more often than not, you're going to look at worst case scenario. Like the worst case was that that X wasn't in the list and we had to exhaust every possibility. Right? Okay. So I guess that will be it for today's lecture. I want to give you time to make sure that you're caught up on my other YouTube videos involving algorithms. And then also start reading through chapter 11. And I would like it if you, let's see. There's a video. This video, P versus NP in the Computational Complexity Zoo. Watch this. It's really, really interesting, and it will shed light on one of the most famous problems in all of computer science and mathematics. So yeah, P versus NP in the Computational Complexity Zoo. Okay, that'll be it for today. I have some work to do for this class involving the assignments I mentioned earlier. So yeah, everyone stay safe, and I will see you guys on Thursday.